Today's topic is the hash functions, cryptographic hash functions. Generally, why we are using the hash function in the cryptography? The sender can send a message to other person. A person can send a message to other person uh, to ensure that message is not modified in the transmission. For that purpose, the sender first sends his message to the hash function. The hash function performing the operation on the message and produces the hash value, the equivalent hash value of the given message. That is called message digest. Message digest. This is just like a document with the fingerprint. So message digest means the message after the hash function is the message digest. Now the person can send that message digest to, that message digest is also called as the modification detection code, MDC. That is useful for the message integrity. Message digest code is useful, detection code is useful for ensuring the message integrity. What is the message integrity? Message integrity means the message should not be modified in the transmission by some attacker. That is assurance is called data integrity. Sometimes we also need the message authenticity. That means the receiver should know the authenticate person who is sending that message. That information, that personal information should be known by the receiver. That is called message authentication. Message authentication means this message was received from so and so person. If it receives from, is that message received from authenticated person or not? That is the message authentication. That message authentication also done by the hash function by sending the actual plain text message along with some key to the hash function. That hash function then produces the message authentication code, MAC. Then the recipient side, the receiver can use that message authentication code whether for identifying the authentication of the message. So this is the use of the hash function. So actually this cryptographic hash function H, here we can assume it is the H, accepts any hash function, any cryptographic hash function accepts the variable length block of data. The variable length block of data. That means the input to the hash function is the variable length size message. That means you can send any size of any length of message to the hash function. So a hash function accepts the variable length size message, but it produces only, that hash function produces only a fixed size hash value. It produces only a fixed size hash value. For example, consider this diagram. This is the cryptographic hash generation. This is the hash function. Assuming this is the hash function, the input to the hash function is variable length message, variable length size message. M is the message. The size of this message is any size, any size. Sometimes it is 10 bits size or 100 bit size, 512 bit size, any variable length message. But the hash function, the output of the hash function is the equivalent hash value to the message with fixed length. This is the fixed length output. So every hash function accepts variable length message but produces the fixed length hash value to the message. Generally, we have two familiar cryptographic hash algorithms. They are SHA, SHA-512 algorithm, Whirlpool algorithm. There are two. There are so many cryptographic hash algorithms, but these are most promising cryptographic hash algorithms. SHA-512 algorithm and Whirlpool algorithm. Both are the cryptographic hash algorithms. Now, here we are using two types of schemes. One type of scheme is the iterated hash function. What is the meaning of the iterated hash function? That means generally every cryptographic hash function needs to create a fixed length output. Every cryptographic hash function must gives a fixed length output, even though it takes the variable size message. That means the hash function must accept the fixed size, must accept the variable that hash function should contains the capability to accept the variable size message. But the actual function is that actual hash function is designed to accept the fixed size input. Generally, every hash function is designed to accept the fixed size message as input. But by performing, that means by performing the same hash function number of times, that hash function can accept the variable length size message but produces only the fixed length output. So the fixed size hash function is referred to as, generally the fixed size hash function is referred to as compressed function. Compressed function means a function which takes some m bits size message but produces some n bits output, where m should be greater than n. That's why it is called compressed hash function. So if you see this architecture, here, assume this is the compressed function. It accepts some arbitrary length input message m. It accepts the message m and produces this function produces some result that is called as intermediate value. For the first time it gives some intermediate value, then after the first output of the compression function, that first output again send back to the hash function iteration, that is called iteration for the next iteration. So now this hash function, this compression function accepts the variable size, that means it accepts the next block of the message and this intermediate result of the previous function. The both are working in the compression function. Again it gives some result, then this result, the output, this is intermediate result for the second time. The second result is also sent back to the hash function. Now it takes the third block from the message and performs some certain hash function, then it gives some result. So like this, so it repeats till all the blocks are, it repeats till all the blocks are completed in the message. Suppose if the message M contains 10 blocks, this compression function repeats 10 times. First time it takes the first block and gives one output. That intermediate output is again sent back to the compression function. It takes the second block from the message and the previous output. Both are on both this data, it performs the hash function and gives the second result. Again that second result is sent back to the hash function and it takes the third block. So that means every next block of the message, every block, for example every block of I of the message also takes the intermediate output of the I minus 1 iteration, I minus 1. That means if it takes, this message takes the fourth block, it takes the third time output, third iteration output as the input and the fourth block. Like this, this compression performs. So finally, after ending all the blocks in the message, it gives the n bit fixed length output. So like this, this compressor function will work. The compressor function will work iteratively, number of times, even though message is arbitrary length size. We have another scheme that is called Merkel-Damgard scheme. Merkel-Damgard scheme. This is also iterated hash function. Iterated hash function, as I explained before. This is also iterated hash function that is collision resistant. Mainly in the hash function, generally sometimes the same message, sometimes the two different messages can have the same hash value. At that time some collision will occur, but we need the collision resistant. That means collision should not occur in the hash function. So here Merkel-Damgard scheme is iterated hash function that is collision resistant. This scheme is mainly basis for many cryptographic hash functions today. This is the basis for many cryptographic hash functions today. Now, if you observe this working style of the Merkel-Damgard scheme, you see this diagram. We have we have this is assume this is our original message, and this is divided, assuming this original message is divided into some blocks. The entire message is divided into some some blocks with equal size. That means, for example, M1, this is the entire message. This is the entire message. The first n bits, the first n bits is the block 1. This is the block 1. We can say this is M1. M1 is first block of the original message with n bits size. M2 is the second block of the message with the same size, n bits size only. M2 is another block and M3 is another block. Till MT minus 1, that means the last but one is also the equal size block. Sometimes the last block we need to add some of the bits to the last block if that block contains less number of bits than n. Suppose if the last, for example, the block size n value is, assume the each block size of the message is 1024 bits. But after dividing the entire original message into equal parts, 1024 size blocks, the last block may be less than 1024. Suppose if the last block contains only 1000 bits, you need to pad, that means add 24 more bits to the last block. That is called padding, to make the last block also the size of 1024 bits. So generally at the time of dividing the original message into equal size blocks, maybe the last block may be less than its block size. At that time you need to add some of the bits to the last block to make it the same block size. That is the padding. Now we assume we have T blocks. Our original message is divided into T blocks, M1, M2, M3 up to MT. MT is the last block of the message. Now assume this is the compressed function, hash function. This is another compressed function. This is all are the F indicates the compression function. Now consider the first time. The first block M1 is sent to the compressed function. The first at the first step, the compression function, for the compression function, you also need to send an initial hash value of size m bits. Assume here h0 is some initial value of the hash, some initial hash value, So the first compression function takes the first block message and it takes some initial hash value h0. So after performing the operation on, after performing the first compression function on this M1 and H0, the first function produces the first hash value output H1. This H1, what is the H1 here? H1 is the output of the first compression function. This is the first compression function. The output of the first compression function is H1. How we have calculated the H1? H1 is calculated as H1 is equal the compression functioning on M1 and the previous initial hash value h0. So this is the h1. Now come to the h2, the second compression function. The second compression function takes the m2 and it takes the previous output of the compression function, that is the h1. So h2, the second compression function f, takes m2 and the previous output of the compression function h1 and produces the h2 as the output. So how we have calculated the h2 second hash value? H2 is equal to the compression function works on the, it takes message 2 and its previous output h1. Like that, the last compressed function, takes, assume this is the t compression function, it takes mt as the block, empty block, and its previous output is ht minus 1, and produces ht block of m bits. See, this ht is the message digest. This is the final output, message digest. So how we have calculated this ht? Ht is calculated with the function of mt comma ht minus 1. Like that, for every compression function operates on hi minus 1, that means previous output of the compressor function and the current block of the message to create the hi. So hi is equal, this is the function. So hi is equal compressed function on, it takes mi block and previous compressed function hi minus 1 hash value. So this is the way of working the compressed function. This style of working, that means every compressed function takes the block, the current block from the message, and it takes the output hash value from its previous compressor function. So this type of working is called Merkle-Damgard scheme. So generally, there are different types of hash functions available. Several hash functions were designed, generally several hash functions were designed by Ron Rivers. These are, the first version is MD. MD means message digest. The second one is MD2. Its next advanced version is MD4 and MD5, like that. There are different hash functions called MD, MD2, MD4, MD5. Generally, MD5 is the latest one. It takes blocks of size 512 bits. It takes, MD5 is the hash function. It takes different blocks of the message of size 512 bits, but this MD5 produces the output of size 128 bits. Now it produces, this hash function produces only the 128 bits size digest, message digest. But this 128 size digest is too small to resist collision attack. Generally, the output of the hash function should be more. Since it's the output to message digest size is 128 bits, the 128 bit size digest is too small to resist the collisions. That's why we can use another version of the MD5, that is the secure hash algorithm. Secure hash algorithm. This is advanced, or it is similar to the MD5 secure hash function. In shortcut, it is called SHA, secure hash algorithm. SHA originally designed by NIST and NSA in 1993. SHA was revised in 1995 as SHA-1 version, SHA-1 version. Additionally, we have 3 additional versions of the SHA. That is, they are called SHA-256, SHA-384, SHA-512. There are different versions of the SHA algorithm. But every SHA algorithm, its structure and working style is similar to the SHA1 only. All are working with the similar concept of the MD5. MD5. If you compare all the SHA versions hash algorithms, this is the comparison of the SHA algorithm. For example, we have SHA1 algorithm. Its advanced is SHA224, SHA256, SHA384, SHA512. There are different secure hash algorithms. This generally the last 512. This indicates the message digest size, the output size. For example, SHA produces the output of the message digest of size 512 bytes. If the SHA algorithm or hash function produces the output of size 384, this algorithm is SHA 384, like that. So this 224, 250, this indicates the message digest size, output size of the function. So if you compare all these, so SHA1, SHA224, all. So the message digest size, that means the output size of the SHA1 is 160 bits. SHA224 size is 224 bits. It's a 256, SHA256. SHA384 is 384. But the output size of the SHA512 is 512 size. This is the highest, the output size is highest value. So this is more secure. And the message size should be the input message size, original message size should be less than 2 power 64 in all the cases. Here in this algorithm message size should not increase 2 power 64, here also 264, 2 power 64. But in SHA 384 the message size can be less than 200, 182 power 128 bits. But in the case of SHA 512 bits, the message size should not increase 2 power 128 bits. Actually 2 power 128 bits means its size is very large size. If you convert this value, its message size is, its value is very biggest value. So this size is enough. We cannot enter more than this size also. That's why the SHA 512 algorithm is the advanced, or it is useful algorithm for us. And the block size, it converts the entire message into number of blocks, and the block size of SHA1 is 512, here 512. But here in SHA 384 and 512, SHA 512 is the block size is 5024. What is block size? That means the entire message, assume this is the entire message, this must be divided into number of blocks, and the block size of the message is generally in previous algorithms 512 bytes, but in SHA 384 and SHA 512 its size is 1024. And word size, and each block can contains each block of the message. Each block, a message is divided into number of blocks, and each block may contains the words. The word size is in these algorithms is 32 bits, is 32 bits, 32, but here 64 bits. And the number of rounds or number of steps used in these algorithms, number of steps or number of rounds used in these algorithms is, it is 80 rounds, 64 rounds, 64 rounds, 80 rounds. So in number of iterations, number of rounds in these algorithms is 80, 64, 64, 80 and 80. So this is the comparison of all the SHA algorithms. Among these algorithms, SHA 512 is the more popular hashing algorithm. Okay, I will stop today.